Well, good morning on this chilly, but at least sunny morning. Hope everyone is doing well. Just a few reminders to start. If not, we'll move back to the lecture on distribution systems, and we left off looking at storage tanks. And as I mentioned, there are multiple types of storage tanks. We can have a ground level tank. Those of you that have done the scavenger hunt should have found a ground level tank. Anybody want to weigh in? Where's the ground level tank that you found? Lansing Board of Water and Light. So you should have found one, exactly, the Lansing Dye water plant. So that has a ground level tank. You can also have a buried tank. You saw a picture of that yesterday in tutorial that Mike Silsby showed you, and that how the 1 million gallon tank at Michigan State was buried, located just west of the engineering building. For smaller communities, typically less than about 600 people, you can have a hydropneumatic tank, and this is a tank that's pressurized with air, and that provides the pressure. You have elevated tanks, and you saw the photos of the new MSU plant, or you can have what is referred to as a standpipe, and a standpipe is essentially just an elevated tank, but the height is much greater than the width or diameter of the tank. So at this point, let's move to looking at a YouTube video on storage tanks and distribution systems. Okay, so this video starts out, and I'm not going to play the entire video. I'll provide you the link in LonCappa to the video. But let's just go back a little bit. So it talks about using pumps to provide water for a community.
Later. Let's say you're the owner of a public water system. You found a source of water of sufficient quantity for your customers. You found a way to clean that water so it's safe for them to use. And now it's time to send the water on its way. There are a few ways we can get water from one place to another. One of them is just to carry it there. Whether it's on the back of an animal or on a truck or a bottle in your backpack, we still physically carry water all the time. But it's usually not the most efficient way. The first infrastructure dedicated to water conveyance was the open channel. Whether in a ditch, canal, or aqueduct, the water is carried by gravity, sometimes over very long distances. We still use open channels to carry water for irrigation and drainage, but they have some disadvantages as well. The water is exposed to pollution and contamination. Channels bisect the land, making it difficult to get across. And the water can only flow to areas of lower elevation than where it started. And that last one's a big disadvantage, especially if you're trying to deliver water to an area with hills or mountains. So most public water systems today rely on pipes for distribution. Simply putting a top on an open channel allows us to take advantage of pressure to move fluids where we want them to go. Just like electrons in a wire flow from high voltage to low voltage, a fluid in a pipe will flow from high pressure to low pressure. So if you raise the pressure at one end of a pipe, you can send your clean water to anywhere you want it to go. And how do you raise the pressure of water? With a pump. A pump is a device that moves fluids. In some cases, a pump literally lifts the fluid to a higher elevation, but in most cases, a pump imparts energy to a fluid by raising its pressure. And pumps, especially the size of pumps that serve entire cities, are expensive. So if you're tasked with choosing the size of pump that you need for your public water system, what do? Maybe you measure the amount of water that a city uses in a given day and select a pump that can match that flow rate. Let's see how that would work. It's midnight in your city and most of your water customers are asleep. Besides the industrial customers that run 24/7, water demands are minimal, and your pump is having no trouble meeting them. But around 5 a.m., automated sprinkler systems start kicking in. Around 6 a.m., people start waking up, taking showers, brushing their teeth, cooking breakfast, all things that require water. And it doesn't take long before the water demand exceeds the capacity of your pump. Almost right off the bat, your new pump can't meet your system demand because it was only sized for the average. Water demand in large urban areas can vary significantly over the course of a normal day, with a peak hourly demand, usually in the morning or evening, sometimes being as much as 5 times the average daily demand. So if you're trying to meet your customers' water needs using just pumps, instead of just one, you might need as many as 5 pumps, or one huge pump that can do the work of 5. And not only that, you'll have to be constantly cycling the pumps on and off to meet the variable demand, increasing the wear and tear on your equipment. And here's where storage comes in. Let's add a water tower to the system and try this experiment again. It's midnight and demand is low, but your pump is running full wide open. Instead of water flowing to customers, it's flowing into your water tower, filling the tank slowly but surely. As morning comes and demand starts to increase, your pump continues running. It's not able to meet the demand on its own, but the stored water in the tank is making up the difference. All your customers are getting the water they need. As people start their day, demand again drops below average, but the pump keeps running and the extra flow goes into the tank. Demand again begins to spike as residents of the city start cooking dinner, taking baths, and watering the plants. All this extra water use drains the tank again before most people go to bed and the cycle starts again. It's pretty easy to see how storage makes your water system more efficient.
So hopefully you can still hear me when I just changed that. If not, please let me know. Okay, great. So just to kind of give you a sense of why we use storage, and you can see that in terms of the pumping. Another thing that they didn't mention here is that you're often pumping at night to fill the tower. Energy is typically cheaper at night, so you can save money by simply being able to fill the tank at low energy demand times and then use the stored water during the high energy demand. Now, they go on right in this part talking about essentially a city where all the homes are at the same elevation. Let's look at what happens if that isn't the case.
Relationship between depth and pressure. It just happens to be confined within a series of pipes. So you can imagine a water distribution system as a virtual ocean under which we all live, and the water surface in elevated storage tanks represents the surface of the
So that surface is the hydraulic grade line.
virtual ocean. Imagining a water system this way makes it easy to see the challenge of delivering water to customers at the right pressure. If our cities were flat, this would be pretty simple. All the buildings would sit at the same depth in the virtual ocean. But most areas have at least some amount of topographic relief. Customers at low elevations are at the bottom of the virtual ocean, where pressures can be too high. You might think this is a good thing, but plumbing pipes and appliances are only rated to certain pressures, so exceeding those ratings can cause serious damage. Sometimes buildings at low elevations will be equipped with special valves to reduce the pressure. Customers at high elevations will be near the surface of the virtual ocean, having very low water pressure. As I mentioned, this can be not only frustrating, but also lead to contamination of the system. To solve this challenge, many large cities maintain separate distribution systems called pressure zones, each with their own water tower, to serve customers at different elevations within the city. But what happens if you need to serve customers at different elevations in the same location? Tall buildings like skyscrapers can have adequate water pressure on the lower floors, while the higher floors can go up near the surface or even above the virtual ocean in the water distribution system. So instead of relying on city water pressure, most tall buildings use their own pumps to provide water to the upper floors. And some cities like New York even require that each building have its own elevated storage tank. Not every city uses water towers. Some have their entire water supply at a higher elevation, minimizing the need to add pressure to the system. And sometimes it just makes more sense to rely on pumps alone to keep the system up and running.
Hopefully we're back with can hear me? We're back to the slides. So this gives you hopefully some sense of how we move water through a community, why we use elevated tanks. If you're driving around the area, take a look if you're in East Lansing, Meridian Township, take a look and you'll see multiple elevated storage tanks. And each one of those corresponds to the pressure zone. So you'll see that, and you've got pressure zones within the immediate area. It's just a schematic of a storage tank, and you can see that you have storage in the top. There is a riser pipe, and water is pumped up that riser pipe or flows down. And there's also an overflow pipe, and that's in case the pump doesn't shut off. You want to ensure that you're not overflowing the storage. So moving through into distribution systems, we need to talk about corrosion. And corrosion is simply the oxidation of a metal. So in a drinking water system, typically what we're looking at is the oxidation of iron, lead, copper, or zinc. So your metal itself is in a zero valence state, and that metal is then oxidized to typically a +2 charge. One of the things to recognize is that for these metals, corrosion is thermodynamically favorable in the pipe environment, which means as an environmental engineer, if you're working in distribution systems, you're going to spend essentially the rest of your life trying to fight corrosion and trying to prevent it. So in distribution systems, corrosion is caused predominantly by the presence of oxygen or chlorine. It's simply, you can simply think of it as rust. In this case, this is a copper pipe, and the copper is oxidized to produce a cupric oxide, and that's the green color that you see here. So the copper is oxidized, something has to be reduced. We'll look briefly at some of these reactions. In this case, this is a iron pipe. And again, what you see is rust. So that iron has been oxidized to produce a ferric oxide, or in some cases, a ferric hydroxide, depending on how it precipitates. So we can use an electrochemical model of corrosion. As I mentioned, the metallic lead is oxidized. So shown here, we've got a lead pipe. That lead here at PbO in a zero valence state here. So this would be a zero valence state, and that is oxidized to Pb2+. That releases 2 electrons. Something has to be reduced. In the presence of oxygen, so oxygen is our oxidant, it is reduced from 0 to that oxygen has a -2 charge. So it accepts electrons and is reduced. The oxidation occurs at the anode. The reduction occurs at the cathode. Both reactions have to occur, and there has to be some transfer of electrons in order for this to occur. Now in 481, Dr. Davies is going to, for those of you in 481, Dr. Davies will spend a lot more time today on this. If you downloaded the notes before last night, you'll see that they're slightly different today, and that's because much of the notes that I had previously I gave to Dr. Davies. He'll use those today. I will also post his lecture. So you have a little bit more information on the chemistry of corrosion. We're going to focus predominantly today on the engineering. Similar reactions can happen with an iron pipe. So you see here we have an iron pipe. Again, we have the oxidation of iron. It starts out in zero valence state. It's oxidized to Fe2+. It produces a ferric oxide, releases 2 protons, and as shown here, it is something has to be reduced. It's donating electrons to oxygen. So that oxygen is reduced from O2, which is a valence state of 0, to oxygen in water, which has a oxidation state of 2-. And that occurs at the cathode. And that forms the rust that you saw on that one pipe. Now, we also talk about galvanic corrosion. And here we're looking at a situation where we have 2 different metals. So they're what we refer to as dissimilar metals, and they're in physical contact with one another. If there is a transfer of electrons, then one can be reduced and one can be oxidized. And you see that here. So in this case, what we have is we have an iron pipe here. We have a copper pipe here. So we have dissimilar metals, and those metals can react. So what happens here is we have oxidation at the anode, we have reduction at the cathode. So copper 2+ is reduced to copper 0, essentially plated out, and the iron is oxidized to form this rust. Similarly, if we have a copper pipe connected to a lead pipe, you can see that the lead is oxidized, it's releasing electrons. Those electrons can be donated to copper, and the copper is reduced. So we have a reduction reaction at the cathode and an oxidation at the anode. Often you'll see the term used with active. So in terms of metals being most active or least active. And you can see it in the table here. So magnesium being the most active, if you actually take a piece of magnesium and you throw it in water, you will have a very violent reaction. It is extremely active. Zinc is more active than iron. So that means that if you have zinc, so if we have a zinc and an iron connection, then the zinc will most likely be oxidized, the iron would be reduced. If we have iron and copper, then the iron is the one that is most likely to be oxidized because it's the easier one to oxidize, and the copper would be reduced. So that's what we mean by dissimilar metals. And you can see in these images here, we start out with an aluminum bolt and a copper nut. In this case, we have copper bolt and a steel nut, and we have a steel bolt and a copper nut. And you can see in the case here, it's really obvious. In this one, you see the rust on the steel. Okay. So it's the steel that's being oxidized. Here is a steel bolt and with a copper nut, and you can see the rust right here. So again, you can see the steel being oxidized. And it's a little bit harder to see here. And we've got aluminum and a copper. And it's the aluminum that is being oxidized here. This is an image from a pipe autopsy that was done a number of years ago in Holmes Hall. Holmes Hall has a reverse osmosis unit, and we mentioned yesterday about how many of the residence halls have softening units at the point of entry. Holmes had an RO unit. The RO unit essentially softens the water to 0 hardness. Now, both of these pipes are before sandblasting. This pipe here is before the RO unit, and this pipe here is after the RO unit. So what's happening here? Basically corrosion. So these are referred to as tubercles. What is happening is you produce a water that has almost no mineral content to it. As a result, any oxygen in that water, if there is a disinfectant in that water, that is able to come in contact with the raw metal. That results in a significant amount of oxidation of the metal itself, and you end up with an iron pipe with these types of tubercle formations. If these break off, they're very brittle, and if they break off, then you end up with red water incidents in the system. These are the pipes after sandblasting, and what I want you to do is look at the thickness of the pipe, and then I want you to look at the thickness of the pipe here. So what's happening? And I'll answer the red water alert question in a second, but what's happening right here? What do you observe? And what would happen if we allowed this to continue? What's happening is corrosion, and it's actually dissolving the pipe. So if we allow this to continue, eventually you can see how thin this is here. Eventually, you will have leaks in the system. So the pipe is wearing away. Question is, what happens? Is that what happens with red alerts? One of the problems is you end up with where you have cast iron pipes in the distribution system, and you have these tubercle formations. This iron just gets released. So what they do at MSU is they typically flush the system to try and remove the iron deposits from the pipe in order to clear away that material. So essentially you have a period of time where you have this red water, and then hopefully after the pipe is flushed, you now have clear water again. So that's what's happening. This is not supposed to happen. This is not desirable. And one of the ways to avoid this happening is to have a bypass. So for instance, here is our raw water. I'll call it raw water to the building. Okay, so this is the entry. here is the RO unit. Instead of treating all of the water, you bypass some of the water. So for instance, now you end up with a hardness of about 100 milligrams per liter as calcium carbonate. And that water is far less corrosive than the water that has essentially zero, which is the situation that they had in this situation. And this is a similar situation in a number of other res halls. I have photos from, I think it was Holden, a couple other residence halls that were using the same sort of process where they had an RO when they didn't have bypass. Now, we can prevent corrosion by a number of means. We can use cathodic protection, and there you actually apply a voltage to the pipe. This is typically done to protect the outside of pipe. So for instance, if your pipe is flowing through a wetland, that sediment will often be anoxic. And because it's anoxic, it has a significant potential for corrosion. So there may be a voltage applied to that pipe in order to try and prevent corrosion of the outside pipe. Also have passive corrosion. This is very common in your hot water heater, where you have a sacrificial cathode. So for instance, zinc is more easily oxidized than iron. So if we have a zinc, so we have a zinc metal in the hot water heater, the idea is that that zinc corrodes, protecting the hot water heater itself. Now we also have passivation, and this is what we rely on predominantly in drinking water systems. We're relying on forming some sort of a coating on the pipe surface to prevent the oxidant from reaching it. So shown here, we have a lead pipe. So this is our lead pipe. And if we have oxidation, then the lead is oxidized from Pb0 to Pb2 plus. The oxidant that's reduced is oxygen, and that is reduced to 2 minus. Now, if we can create a coating around the inside of the pipe, that prevents the transfer of electrons. And if we can prevent the transfer of electrons, we can prevent corrosion. And that's the whole concept of passivation. So what we're doing is we're coating the surface of a material so that we can prevent a corrosion cell from forming. We're preventing the transfer of electrons. Now we can control that by the formation of calcium carbonate. We talked about this in terms of LSI, the Langmuir saturation index. So what in this case we're doing is we're looking at, remember we wanted a water that had a slightly positive LSI, and that means that we're slightly oversaturated with calcium carbonate, and that means that on the inside of our pipe, we will form a calcium carbonate scale. We can also add phosphate, and Tom mentioned this yesterday, where he was talking about the pipe rig experiments that they're doing to try and optimize the concentration of phosphate that they're adding in order to prevent corrosion in the distribution system. And we can add silicate. So for example, if we look at a lead pipe, if carbonate is present, then you will form carbonate minerals on the inside of the surface. If phosphate is present, then you can form lead phosphate minerals. And these minerals are less soluble than carbonate minerals, so they're more protective. If the chlorine levels are high and the organic matter is low, you can form lead 4 oxides, and these are extremely insoluble. So what you see here is a passivated pipe. This has some, looks like a white coating in here. It's actually irregular. And this is likely to be either a lead hydroxide or a lead carbonate. We don't know based on the photo. But it doesn't completely cover and coat the inside. And that would allow the potential contact of your oxidant, being the disinfectant or oxygen, with the metal. Here it is a yellow color. This is likely a lead phosphate coating on the inside, and it's a much more uniform coating. So what we're doing is we're precipitating in this case, the lead phosphate, to try and protect the pipe from further corrosion. So typically, when we're looking at passivating pipes in the water industry, we're looking at either adding phosphates or adding silicates. And when we're looking at adding phosphates, it's important to recognize that typically there are 2 types of phosphates we add: orthophosphate and polyphosphate. And as Tom mentioned yesterday, what they're looking at MSU is a formulation of ortho and phosphate, ortho and polyphosphate. Now, orthophosphate is used for corrosion control. Polyphosphate is used for sequestration. We'll explain that in just a bit. And it's also important to recognize that over time, polyphosphate with its long chain of phosphates does break down to form orthophosphate. So when we're looking at these, we can compare orthophosphate with polyphosphate and these blends. The blends are proprietary and they vary significantly from one manufacturer to another. So if we're looking at orthophosphate, it is simply PO4 3-. It comes in a liquid, comes in a powder, and it's used for corrosion control. If you're in 480, what you measured in the phosphate lab is orthophosphate. Now, polyphosphate is a chain of phosphate molecules. Here, you're looking at iron sequestration. So you're looking at complexing the iron. You can also complex the calcium to keep it into solution, to flush it from the system. So with polyphosphate, you're not looking at passivation. Here, you're looking at passivation. And the last statement really just pertains to the requires digestion, pertains to how we analyze for polyphosphate. Even if you, for instance, buy a 30-70 or a 70-30 blend of orthopoly, and you simply change suppliers, they will behave differently in the system, which is why we run these pipe rigs, because it's very, very difficult to predict a priori how that system will behave and whether or not we'll see increased corrosion, increased lead concentrations, increased copper concentrations until we actually do the testing. And it's for that reason that MSU was required by Eagle to run those pipe rigs that you saw where they're testing the rates of corrosion. Now, in terms of the phosphate levels, NSF is NSF International. It was a National Sanitation Foundation. It is basically now just NSF International. It is a private organization. If you, for instance, go to a hardware store, you can look on Amazon for a filter for your kitchen faucet, say to remove lead. You'll see it will say NSF certified, hopefully, or it won't. And basically that just means that it has gone through a series of tests that are formulated by this organization, and it meets the testing criteria under those conditions. They will also specify a maximum dose, and they specify maximum doses for anionic polymers, cationic polymers, for phosphates. The other thing you need to think about is what impact does this have on the wastewater treatment plant? So for instance, in Flint, they have been adding phosphate to their water. It's about 3 milligrams per liter. I'm not sure the formulation. Initially, it was actually phosphate or phosphoric acid. And I'm not sure what they're doing right now. But so initially, it was 3 milligrams per liter of phosphoric acid that they were adding. That drinking water goes to the wastewater treatment plant. The wastewater treatment plant has phosphorus limits. So one of the things that one has to do is work with the wastewater treatment plant so that they're aware and prepared to deal with perhaps an increase in the phosphorus level in the influent water. And then they can deal with that in terms of treating it. For corrosion control, typically we use about 1 to 3 milligrams per liter of orthophosphate. For sequestration, the doses will vary significantly. When we look at silicates, again, not all silicates are equal. The silicate chemistry is pretty tricky. I don't know of any plants in the US that are using silicate. I know there have been a number of studies done, but I'm not aware of any plant that is using silicate. It's used more often in hot water conditions. So for example, in boilers and automotive antifreeze as a corrosion inhibitor there. We have a number of indices that we can use to try and assess the level of corrosion that might exist. LSI really is not a corrosion inhibitor. It assesses the degree of saturation with respect to calcium carbonate. And we've used that. The chlorine to sulfate mass ratio is also used, and that's because it appears that chlorine, and this is we're looking at chloride, okay? Chloride can promote corrosion because it promotes the transfer of electrons, and then we have the Larson-Skold Index. So the CSMR is simply the chloride to sulfate mass ratio. It is the concentration of chloride in milligrams per liter divided by the concentration of sulfate in milligrams per liter. And based on an empirical survey of a large number of utilities, what they found was that 100% of utilities that had a CSMR less than 0.58 met this action limit of 15 micrograms of lead per liter. But only 36% met the action limit if their CSMR was greater than 0.58. So it doesn't mean that you will definitely exceed the action limit for lead, but it implies that lead corrosion is more likely to be problematic at a higher CSMR. If your alkalinity is less than 50, then the CMSR should be less than 0.2. Just to give you in Flint, after treatment, the CSMR in Flint ranged from about 2.5 to 3.2. So significant increase in the CSMR. That was because of the ferric chloride that was added, which releases 3 chloride ions for every 1 mole of ferric chloride that's added, or 3 moles of chloride, 3 moles of chloride for every mole of ferric chloride that's added. And then the last index is the Larson-Skold Index, and this was created for mild steel. It, again, is not a perfect index, but it does provide us some indication. And this is the sum of the chloride. Notice your units or equivalents per liter. And basically, it's divided by the alkalinity. And again, the premise here is that the chlorides and sulfates may interfere with the natural passivation, and they help promote electron transfer, which is necessary in order to have corrosion. So the question is, what do I mean by met? Okay, so this action limit is a treatment technology limit. And the way the lead and copper rule is written is you monitor for lead every 3 years or more often if you change the system. So you're looking at the concentration of lead in your drinking water in the homes in a particular, it's a set number of samples based on population, and you're sampling the systems that are most likely to have lead. So you're targeting homes with predominantly lead service lines. What you then do, for instance, if you're looking at a large system, you have to sample 100 homes, and it's typically within about a 6-month period. And what you determine is the 90th percentile. So that means that 90% of the samples have a concentration less than or equal to 15 parts per billion of lead. There is no upper limit on that other 10% of the samples. If you meet that, then you meet the regulatory limit and there's no action needed. If you do not meet it, then you have not achieved optimal corrosion control, and then you must work typically with the state agency that has primacy to determine what needs to be done, what modifications in the system need to be done in order to optimize corrosion control. So hopefully that helps in terms of what I mean by meeting the action limit. I know I've gone over, but I think I've only got like one more slide. I'm not going to spend a lot of time. This is just the direct measurements for assessing corrosion. Notice, if you haven't watched yesterday's tutorial, Tom talks about this. In these rigs, they have coupons, and what they're doing is they're looking at weight loss. So they have a rig system set up with coupons in the circulating pipe. They can also look at the pipe itself. They can look at corrosion products to try and assess whether they have corrosion, and they can use various surface techniques to analyze the deposit. So all of this is done to assess corrosion. So I will end here. Happy to stay on and answer any questions about distribution systems. Otherwise, I will see you on Friday. After 481, I will, and I get Dr. Davies' lecture from 481 today, I will also post that and the link to that, so you'll have more chemistry, the more chemistry aspect of corrosion than what I've covered here. So thank you.